All right. So we've been discussing different things so far. We've looked at symmetry. From symmetry, we've invoked the concept of point groups. From point groups, we've moved on to crystal systems. We've continued our journey and transitioned into the concept of Brave lattices. And we've also motivated the concept of space groups. So, point groups deal with the external morphology of crystals. Crystal systems are about the shape of the unit cell. Brave lattice are the unit cell plus the various kinds of centering. And space group deals with the arrangement of atoms inside a crystal, which conforms to the various symmetry operations. So this is all that we've discussed so far. Now what we would like to do today is we would like to gather all of these concepts, put them together, and then develop the idea of how crystal structures are actually made. And we'll do that by looking at certain examples. So before I proceed, are there any questions that you would like me to answer? All right, so far so good. So let's start off by looking at some simple structures. Consider the element polonium. Now, polonium is a primitive cubic lattice. So, in order to define a crystal structure, there are different ways to look at it. The simplest is to define your lattice type, one of the 14 Bravais lattices, primitive cubic lattice, and define the motif or the basis. And the basis here is a polonium atom at 0, 0, 0. Now, what does this mean? This means that first of all, we will draw the primitive cubic lattice. And my convention is this, I will call this x-axis, I will call this the y-axis, and I will call this the z-axis. Now, my first question is how many points are in this unit cell?
One.
There's just one point, and that one point is at the corner of the unit cell. And just for the sake of completion, what I would like to do, I would like to identify this point over here, and I put a polonium atom here. Okay. So this is the unit cell of the crystal structure of polonium. And this location 0, 0, 0 is with respect to each lattice point. So the lattice point that I've taken is at the origin. This I've defined to be the origin, and I put a polonium atom there. And just for the sake of completeness, I could put polonium atoms at all the edges. And consider that the relative contribution or the participation of each atom in the unit cell is of the order of 1 by 8, because each corner is being shared by 8 neighboring unit cells. So this is the crystal structure of polonium. Okay, and I've defined a lattice type, and I've defined a basis or a motif, and I've picked up that motif or basis and placed it at each and every point of the unit cell. So the lattice and the basis together form the crystal structure. Now, let's look at another example. And then we'll move on to space groups. So I'm giving you the simplest explanation so far. Consider the compound, the ionic compound cesium chloride. Now, cesium and chlorine are in the ratio 1 to 1. So, cesium chloride also has a primitive. So, let me not write down the word primitive so far. Let me just first of all write the crystal lattice. The lattice is cubic. Let me first draw the lattice. Here is the cubic lattice. And let me go the other way around. Let me first draw the structure and then we'll determine what type of lattice is it. Okay. So I draw the structure. I put a cesium atom at each of the 8 corners. So this black represents cesium. And I put a chlorine in the body center. Okay. Now, is this a legitimate structure? Are cesium and chlorine in the ratio 1 to 1?
Yes.
Yes, they are, because there's one cesium atom in the unit cell and one chlorine atom. The one chlorine atom is totally enclosed within the unit cell, so it doesn't leak out of the unit cell and go into a neighboring unit cell. You can always adjust the origin of your unit cell so that the edges coincide with the lattice vectors and so on. But there is one chlorine atom and one cesium atom, so the atoms are in the proper stoichiometric ratio. So this is the crystal structure of cesium chloride. Now my question is, it's a cubic unit cell, but what Bravais lattice is it? The cubic can have four kinds of Bravais lattices: a primitive, body-centered, face-centered. It can have three, sorry. So what kind is it?
Body centered.
Body-centered.
Cubic.
All right. So the immediate response is that this is a body-centered crystal structure, a body-centered Bravais lattice, sorry. But that is incorrect. It is in fact a primitive unit cell with a basis defined by cesium at 0, 0, 0 and chlorine at half, 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 where half, half, half are the fractional coordinates. So what you would like, so it's not a body-centered structure. It's not a body-centered lattice type, rather it's a primitive lattice type. And what you could do is you could simply take one point of the unit cell. Let's take the origin and put a cesium here and put a chlorine at the location 1 half, 1 half, 1 half, which is the body center. So this duo of atoms, a cesium and a chlorine atom bonded together, they form your basis. So you take any point of this lattice, any point of this lattice. Say I were to take this point. I would take any vertex whatsoever and put a cesium at that point and a chlorine atom, which makes a vector 1 half A plus 1 half B plus 1 half C with respect to that lattice point. And all the lattice points have to be totally equivalent. Lattice points are related by translational vectors. So this is really a primitive Bravais lattice with cesium and chlorine forming the duet of these atoms forming a motif, and they are placed with the proper orientation with a relative vector which I've written in red over here at each lattice point. Okay, so you get this. Let me turn on the video because we've resumed power here. Let me try to see if I can turn it back on. Just give me a second. Hmm. So teaching online is slightly complicated sometimes, right? Right, so let me start my video. All right, okay. So far, so good. So, any questions, my friends? Now, let's talk about these structures in the language of space groups. Now, when we talk about space groups, we have to talk about the crystal structure, not only the lattice type, but also the motif, the geometrical arrangement of all the atoms that go inside this crystal structure. Now, by the way, if I just draw the unit cell and I put the atoms at the proper locations, at the proper fractional coordinates inside the unit cell, and the unit cell has been drawn to its proper shape with the proper interaxial angles and the proper length ratios of the interaxial vectors, I've defined everything that I need to know about this crystal. Of course, if I forget the surfaces. So, but the alternative description is to look at these crystal structures in the language of space groups. Now, both of these structures that I've drawn belong to a space group whose international symbol is PM 3 bar M. All right. Now, if I look up this space group and see what it means, I need to look up the international tables of crystallography, volume A, which is the compendium of all the 233 space groups. And let me show you what this crystal structure looks like. Uh, here you go. This is the entry of the crystal structure of the space group. Now let's see what we have over here. We have the name of the space group, which is PM3 bar M. Let me backtrack a little bit. Uh, Let me describe a little bit about these entries in the International Tables of Crystallography Handbook. Okay, this is what you get. So let's see how many pages do we have for this space group, which is CMM2. So I can't use my cursor here, by the way, because this is a PDF and I can't seem to open this in my other software, OneNote. So please bear with me on this. If you look at the top left, we have the name of the space group, CMM2. This is in the international notation.
Sir,
B.
I think we're still seeing the OneNote body window.
Okay, all right, okay, just hold on, please. Okay, you can see one note, but now can you see the PDF, the other thing?
Yes, sir.
All right, thank you. But I can't use my cursor here. I'm sorry about that. I need to get some extra time in seeing how to use my cursor here. But let me see if I can. Oh, okay, good. Got it. So this is the name of the space group, CMM2. The first letter represents it's a C-centered lattice, and there are three entries. And by looking at these three entries, I can tell that this is orthorhombic. Okay. The first M shows me that there is a mirror plane perpendicular to the x-axis, The second M also shows me that there is a mirror plane perpendicular to the y-axis, and the third 2 shows me that there is a two-fold rotation axis perpendicular to the along the z-axis. Okay, C2V number 11 is the Schonflies notation of this space group. MM2 is the point group of this space group, and I'll explain what the point group of a space group means. This belongs to the orthorhombic crystal system. Now, all the space groups are also numbered from 1 to 230 for easy reference. So, this space group is number 35. And these are some additional details, CMM2, and there's a Patterson symmetry which has to deal with diffraction, etc. First of all, we have a geometrical representation of, of the various symmetry elements seen along various projections. So if you look at the top left here, this thing, this is the projection looking down the z-axis. And you will observe that there is a two-fold rotation axis here, 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 and so on. And then there are mirror planes. So here is a mirror plane. This mirror plane is perpendicular to the x direction. And here is a mirror plane perpendicular to the y direction. Okay. And there are additional planes that are dashed, shown dashed as well. These are glide planes which are created because of the particular symmetry, but these glide planes are not essential to this structure, so I'm going to ignore them for the time being. All right, so this projection on the top left shows all the symmetry elements in this space group. Then these are projections seen along the various other directions. This diagram here shows how a particular group of atoms is transformed under the action of these symmetry elements. Okay. Then we define an origin. The origin is on the intersection of a mirror plane, and the two-fold rotation axis. So the origin could be this point here. So this is how the space group is defining all the fractional coordinates that precede. Now here we have an asymmetric unit. If I look at the asymmetric unit, x is less than 0 and 1 by 4, and y is this. So if I draw this area here, if I color this area has the locus that x is between 0 and 1 by 4, and y is between 0 and half, and the z is throughout the height of this unit cell. So if I just took the green area and I had all the symmetry elements available to me, I could reproduce the entire unit cell. This is what the asymmetric unit means. Okay. Now here is a listing of the symmetry operations. And remember, it's a C-centered unit cell, which means that the base is also centered. So that's why we have a point at the center of the base. Okay, are you with me on all of this? I'm just describing, I'm walking you through a particular page of the International Tables of Crystallography. With all the ingredients that we've discussed so far, we can now make sense of this table and can get a good understanding of what's going on over here. Okay, then we have a listing of all the symmetry operations. So there, uh, one question I would like to ask is, how many points do we have in a C-centered orthorhombic unit cell? Points, not atoms, just points.
Ten, sir.
G, how many?
10.
10?
सी सेंटर में बेस के ऊपर हम रख सकते हैं ना,
बिल्कुल बेस के ऊपर होंगे,
फिर
तो एक तो
तो
एजेस
10
पे हो गए. How many contribution due to the edges, due to the corners? Just one. Okay, now I
Yes.
settle the base.
ठीक है.
So we just have 2 points per unit cell because this point is shared by with half. The contribution to this unit cell is 1/2 because it's shared across 2 unit cells. So a contribution of half comes from here and a contribution of half comes from here. So there are 2 points per unit cell. Okay. So this image that I've drawn over here, that the crystallographers have drawn over here, this one is just looking down at the base of this crystal lattice. Now, the kind of symmetry operations. So we need to define symmetry operations for points at the origin as for points at the base. So this point is half, half, 0. Because x is half, y is half, and z is half, 0. And these are fractional coordinates. So they are described in terms of relative to the total length of that unit translation vector. All right. So here's a listing of the symmetry operations. Of course, we have no symmetry. We have a two-fold rotation axis about the 0, 0, 0, 0, 0 z axis, which is really this axis here. So this is a two-fold rotation axis. Now remember that we can place atoms inside this unit cell because now we're talking about crystal structures, not just lattices. Then we have an m-fold rotation, which is which intersects the y-axis at 0. So this is our m-fold rotation, m-fold rotation plane, m-fold reflection plane. And here is another m-fold a rotation plane, sorry, a reflection plane. And here is a, another reflection plane, which is perpendicular to the one that I've just drawn here. A reflection plane here, so inadvertently there will also be a reflection pair here. So this is a listing of all the symmetry operations relevant to the origin. Likewise, we have symmetry operations relevant to the other point, to the base centered point as well. So here is another view. Here is what I've discussed already, the asymmetric unit. And now the Wyckoff positions. Let's talk a little bit about the Wyckoff positions. Now, if you look at this space group CMM2, there's a listing of fractional coordinates. So all of this, so what I'm going to discuss now is all of this. Guys, are you with me?
Yes, sir.
All right, okay. So we're going to discuss this part of the space group table. Now, the first entry here is called the multiplicity. Then we have a Wyckoff letter, and then we have the site symmetry. We have two sets of points, one at the origin and one at the base center. Since it's an orthorhombic C-centered unit cell, we need to define the positions of the 2 points at which we are going to place our motifs. Now, we can put atoms at different locations, but We can always only do that if the symmetry operations relevant to this space group are satisfied. They leave that arrangement of atoms in an invariant position. So atoms can only be placed at specific locations. All right. So if an atom is placed at a general location x, y, z anywhere, so let me draw any point here in the lattice. Now this is just a projection view. So if I were to draw my orthorhombic unit cell, and I were to place my atom anywhere, just anywhere inside this unit cell at a coordinates x, y, and height z. So this is where I placed my atom. Then invariably, if the structure belongs to this space group, there should also be a corresponding atom at this location, x bar, y bar, and z, which means at the neighboring unit cell height z. Okay. There should also be an atom at this location and an atom at this location. And there are 8 such points because one is this set and the other is the set obtained by adding these coordinates to these points. So I will also have an x plus half, sorry, y plus half 0, and I need to add these coordinates x bar plus half, y bar plus half 0, z, and so on. So I will have 8 such points. If I place an atom in an arbitrary location x, y, z, then I must have the same atom with the same identity, chemical identity, placed at these 8 locations. So a general position XYZ necessitates that if this structure belongs to this particular space group, it must have the same atom, the same chemical identity placed at 7 other points inside this particular unit cell. So this is the general position of general equivalent positions of atoms inside this unit cell. And we say that the Wyckoff position is 8F. 8 shows the multiplicity, and F is just an arbitrary number. The numbers move, these letters move alphabetically upwards from A, B, C, D, and so on. And the
Sir,
symmetry, yes, please.
what kind of structure will these 8 points form together? I mean, what will be the separation between them?
The separation between them.
I mean, if I join them with lines.
Yeah, it's going to be some structure, some complicated crystal structure.
Okay.
Okay. Likewise, I have these, all of these positions are possible. So I can, now let's look at the bottom row. If I were to have a point at 0, 0, 0, 0, 0, z, so which means I really have a point on this axis here. Let me change the color. So a point on this axis here, anywhere on this axis, here, anywhere on this axis, anywhere on this axis, because all of these 4 points are equivalent. They are just related by translation vectors. Uh, so likewise, any point on the exact axis which bisects goes through the middle of this cell, because I need to do centering as well. So if I have an atom here, its location is 0, 0, z. And there are 2 such locations, one at 0, 0, z, and the other at by obtained by adding these coordinates half, 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 0, which means the center of the base, an axis protruding from the center of the base. So if I have an atom here, I also need to have an atom. So an atom placed An atom placed here will have a corresponding atom placed here. Okay, so the multiplicity of this location is 2, and it's given the Wyckoff symbol A arbitrarily because we're starting off from A, and the symmetry at this location is mm2, which means that there are two mirror planes intersecting one another and a two-fold rotation axis passing through this axis. So this is the symmetry, local point group symmetry of this site, and the fractional coordinates are given. So an atom could be at location 2A. Likewise, an atom could be at location 2B, and two atoms could be at location 2B, four atoms could be at location 4C, and so on. So this is how we define the crystal structure. We look at the Wyckoff table and determine where are atoms inside the crystal structure. What sites do they inhabit? Do they inhabit 2A, 2B, 4C, 4D, 4E, or 8F? And we fill in atoms at these Wyckoff positions. Okay, so you got this? Likewise, any questions here up till this point? By the way, if you look at the nomenclature of space groups, the triclinic space group has the triclinic crystal system has two space groups only, P1 and P1 prime. Monoclinic has more space groups to it. Examples are given here: C2, P2 sub 1 forward slash M. So the characteristic of a monoclinic crystal system is that there is only one two-fold symmetry operation, a two axis or a two bar axis or a two one axis. Orthorhombic is described by three letters or numbers, and each of them could be a 2 or an M or a glide plane or a diagonal plane, because the orthorhombic has two-fold symmetry operations perpendicular to X, Y, and then Z. A tetragonal is identified by having the first symbol 4 or 4 sub 1 or 4 bar followed by something else because it has a four-fold rotation axis. The trigonal is symbolized by having a 3 trigonal or rhombohedral. I can write rhombohedral as well. By having a 3 bar or a 3 screw axis in its first position. The hexagonal likewise has a six-fold rotation axis or a six-fold roto-inversion axis or a six-fold screw operation axis in the first position. And the cubic is identified by having some 3 or 3 bar in the second position. Okay, so the first could be something else. It could be a 2, it could be a 4, it could be a 3, but there is always a three-fold rotation axis along the body diagonal. So the rule is that if there are, if you talk about the cubic, for example, the first symbol or the first number represents what's going on along the cube edge. The second tells us what's going on along the body diagonal, and the third tells us what's going on along the face diagonal. Okay, so there are general rules about nomenclature of these space groups as well. And the first letter always represents the lattice type, whether it's P centered, it's C centered, I centered, F centered, and so on. Yes, Mariam.
So I think the structure that we talked about previously, the CMM2, why do we write it as CMM2 and not just CMM?
Because it's orthorhombic. And when we're talking about orthorhombic, all three axes are distinct from one another. The x-axis is different because the property of orthorhombic is that A need not be equal to B, need not be equal to C. or even though all three angles need to be each equal to 90 degrees. So now A, B, and C are all distinct. Therefore, we need to decide what's going on perpendicular to A, what's going on perpendicular to B, and what's going on perpendicular to C. That's why we need three symbols after, of course, the mention of the centering. Okay.
But sir, doesn't the presence of two mirror planes implicitly imply that implicitly tell us that there is also a two-fold axis of rotation?
But what about this twofold axis of rotation here? So there are cases in which um, that might not be that might not always be true, because the location of the M planes is not clear at the moment. So in the orthorhombic, you need to define what's going on along the third axis, the third distinct axis.
Okay.
You could also have M. Okay. So there's a full notation for CMM2 as well, which is not given in this table, which identifies all the symmetry operations. Okay.
Yes, sir. Thank you.
So here is the ordering of the axis in the point group that I'm mentioning. So if I have a point group 432, it means that there is a four-fold axis of rotation parallel to the cube edge, and it's shown over here. So these axes are parallel to the edges. Then there's a three-fold rotation axis along the body diagonal. Here you go. And then there's a two-fold rotation axis along the face diagonal. So if I were to draw the face diagonal, so I could take this point. They've drawn it by this axis here, okay? So here is a comparison of the screw and the glide planes. So let's now talk about our structures. The polonium and the cesium chloride examples that I've brought up. Let's look at the space group table for PM 3 bar M. And for that, I need to go here probably. All right, so this is the PM 3 bar M space group. Sorry, I'm a bit slow today because I'm not used to marking PDFs. So we're talking about polonium first. If you talk about polonium, there's an atom at the location. If you look at this table of the Wyckoff positions, could you tell me where is our polonium atom? At what site is our polonium atom?
000.
Yes. So the polonium atom is at the Wyckoff position 1A. So this describes the crystal structure. The polonium element belongs to the space group PM 3 bar M. Okay. And the site symmetry here is PM 3 bar M, which means the local point group at this location is M3 bar M. So we can just have one atom placed at the location 0, 0, 0. And that's it. So there is one point per unit cell and there is one atom per unit cell. If you look at cesium chloride on the other hand, So if you look at cesium chloride, by the way, there's a M 3 bar M, so it's a cubic structure. There's a 3 or a 3 bar in the second position after this mentioning of the center. So there's a cesium atom here, and a chlorine exactly here. It's not a body-centered structure. It remains a primitive structure. You can't, okay, and I'll ask you why can't we say it's a body-centered structure? Now, could you identify the location of the atoms, please?
1A
Sir,
and
0, 0,
1B.
0.
Polonium at 1A. Sorry, not
And
polonium. I'm sorry. Sorry, not polonium. Zinc. We're talking here about cesium
cesium
chloride.
chloride.
Cesium at 1A and chlorine at
1B.
1B.
1B, or vice versa. Can we say vice versa?
Yes, sir.
Yes, we can place the chlorine at 1A and cesium at 1A, doesn't really matter. The choice of the origin is arbitrary. But may I ask you, and you might like to raise your hands here, why is this not a body-centered Bravais lattice?
Because there are different atoms in the body center and the corners.
Exactly. It's not, if you talk about a body-centered lattice, you need to put the same motif on each point, whether the point is at the vertex or at the body center. But now we have two different chemical elements placed at the different locations. So it's not a body-centered cubic unit cell. Rather, it is a primitive cubic unit cell, even though apparently for a novice it looks like a body-centered structure. It's not a body-centered structure. Okay. The motif is different. It comprises one cesium atom and one chlorine atom. The cesium atoms are located at location 1A and the chlorine atoms are located at location 1B. Now let's look at yet another structure belonging to the same space group.
सर
जी जी
सर अगर मैंने जो क्लोरीन एटम है इसको प्लेस करना है लैटिस के ऊपर, तो हमने इसका एक मेथड डेवलप किया था जो लेटेस्ट स्ट्रक्चर एक डिफाइन करते हैं, उसके ऊपर हम कन्वोल्यूशन लेते हैं बेसिस के जरिए.
हाँ जी, लेटेस्ट के ऊपर
तो
जी.
हाँ, तो अगर बॉडी सेंटर लेटेस्ट नहीं होगा तो फिर मैं कैसे प्लेस कर सकता हूँ क्लोरीन एटम सेंटर पे?
क्योंकि now your basis is defined by, if you use that approach, your basis is defined by cesium at location 0, 0, 0 and chlorine at location half, half, half. So you draw a vector originating from the cesium and a chlorine atom, which is defined by a position vector given by these coordinates. And at each lattice point, you place this arrow. You place the cesium atom at the origin of the arrow, and you place a chlorine atom at the head of the arrow, and all the arrows are being drawn on the lattice points in the same orientation.
But the chlorine atom is not at any lattice point.
Doesn't matter.
Open.
So that doesn't matter. The lattice point is a placeholder for a big geometrical structure. That could be a single atom, it could be a group of atoms, it could be anything, any motive that you like. The
मतलब
chlorine
क्रिस्टल के
atom.
अंदर एक लेटिस के अंदर हम एटम किसी भी जगह प्लेस कर सकते हैं.
Exactly.
Okay.
XYZ means you can place the atoms anywhere, but not really anywhere in the sense that you need to respect the symmetry elements. So you can place one atom at a location, then look at the symmetry elements and see where other locations must coexist with the atom at that one particular site.
वैसे मतलब मेरे माइंड में तो इंट्यूटिव आइडिया इसका यही था कि कोई क्रिस्टल होगा तो उसके जो एटम्स होते हैं उनको हम आपस में कनेक्ट करते हैं तो एक लेटिस बनता है।
गलत आइडिया ये। Lattice is a
Okay.
placeholder. Lattice is a grid, is a placeholder. So if I were to draw a grid, so let me move back to OneNote for a minute. If I were to draw, say, a grid, and my atoms are, my motif is like this. Suppose I can place my motif here, but it has to be at the same relative position with respect to all the lattice points. I make a crystal structure in this fashion. So I need not place my bases at the lattice point. Okay. What I could now do is I could always change the relative origin. So I could take this lattice, this grid, and displace it to the right. I can always change the position of this, the origin of this lattice. I can always move it around. What is important is the translational vectors. The translational vectors, the orientation which connect one lattice point to another point, they remain invariant. You take a vector, you change the position of the vector, it remains the same vector. It doesn't change.
Okay.
All right. Did I answer your question?
Yes, yes.
Now let's go back to our structures. Let's look at another structure, slightly more complicated, barium titanate. A barium titanate, this kind of structure of the general stoichiometric formula AbO3 is called a perovskite structure. Now the perovskite structures are really important. One of the first high temperature superconductors that were uh, discovered or invented in 1986, yttrium, barium, copper oxide, they belong to this class. Many of the new solar cells that are being made are of the perovskite kind. Many ferroelectrics, piezoelectrics, which find a lot of technological applications, are of the perovskite structure. The perovskite structure, now compared to polonium and cesium chloride, this looks like a complicated structure here, but it belongs to the same space group, P, M, 3 bar M. And what you have are barium atoms at the corners, a titanium at the exact center, and oxygen atoms which engage the the titanium ions and form a kind of an octahedron. Now there are different ways of looking at crystal structures. This is one particular way. So what we could do is, now let's look at PM3 bar M again. So there's a barium atom here. There is a titanium atom here, and then we need oxygen atoms. So the oxygen atoms are at the position 3C. And there are three of them. So there's one barium, one titanium, and three oxygen atoms. And where are the oxygen atoms? They are at the centers of the faces. Look at the coordinates: 0, half, 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 0, half, 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 0. So let's look at this atom here, this oxygen atom. Its location is half, 0, half. So along X, it's not on the outer edge, it's inside the unit cell, and its location is half, 0, half. Likewise, this location is 0, half, half. Okay, and so on. So here we have drawn 6 atoms, but only 3 of them are exclusively inside, because this atom is shared with half with this unit cell and one half with the other unit cell. So this is the barium titanate structure. There are There is barium at the location 1A, titanium at the location 1B, and oxygen at the 3C positions. Okay, and what we could also do is the following. Now, if I look at the space group again, 3C 0 half 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 0 half 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 0. I could draw this structure in another fashion. I could draw. Let's move back to the one note. Talking about barium titanate now. It's cubic. So I'm just looking down the z-axis. So I'm looking at the z projection. The barium here at the edges in the basal plane. There is a titanium in the exact body centered position, even though it's not a body centered lattice, but at the center of the body, there is a titanium at an elevation of 1/2. Okay, so this represents titanium. And then I need 3 oxygen atoms. And the oxygen atoms are at location 3C, which are half. Let me go back and see where the 3C is half 0 half 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 0 and 0 half half. So I go back here, half half 0 half 0 half and 0 half half. So this is my x-axis, this is my y-axis. So I have an oxygen atom at half half 0. So I need an oxygen atom here at elevation 0. I need an oxygen atom here at an elevation half, and I need an oxygen atom here at an elevation 1/2. So this oxygen atom is being shared between two unit cells, and so is this. But this oxygen atom is also being shared by between two unit cells, the current unit cell and the one immediately below it. Okay, so if there is an oxygen atom here, there has to be an oxygen atom here as well, because of the unit translation vector. It needs to be an oxygen atom here as well. And there also needs to be an oxygen atom at the upper base. So if I were to draw this structure and I would like to place the oxygen atoms, I'm just going to draw the oxygen atoms now on this structure. An oxygen atom here, an oxygen atom here, oxygen here, oxygen here. Connect these points. Oxygen here. And here we also have a titanium atom, by the way, a titanium ion to be precise. And all of this forms an octahedron. But it's not an octahedral unit cell, by the way. It's a cubic unit cell. And when we draw the structure, we can draw the structure in many different kinds. One generally draws octahedra surrounding the titanium ion, oxygen octahedra. But the space group description tells us everything. It tells us what symmetry elements exist, what are the Wyckoff positions, where are we going to place the atoms, and so on. All right, so there are more examples that I would like to talk about in the last 10-15 minutes. So any more questions, my friends? So look at this structure here. This is the element iron. Okay, and iron belongs to the space group I, M, 3 bar M. So this is a very popular space group. Many elements and many compounds, they exist in this space group. First of all, by looking at the symbol of the space group, could you tell what kind of Bravil lattice is it?
Body centered.
Body centered. And why is it cubic? How does the notation tell us it's cubic?
There is a 3-bar
Second
There's a
position.
3-bar in the
body
second
diagonal.
position along the body diagonal. All right. And if I look at the space group, I am 3-bar M. Let's see if I, okay, here it is. Here is the Wyckoff table. There are two atoms at the 2a side. One is at 0, 0, 0, and the other one is necessarily at the body centered position as well, which is, we don't want to write the two locations over and over again. We just write one of them and put a half, half, half plus sign to identify that the second relative position of the atom, which may be called the body centered position, is obtained by adding half, half, half to the locations that are written down here. So we have two atoms at the location 2a. That's very simple. This is the iron structure. Okay. Now let's look at our next popular crystal structure. And let me draw a picture of this. So this is the structure. This is what iron looks like. Here are two more structures. Copper, the element copper, and sodium chloride, the crystal of sodium chloride. On the left, we see copper, only copper atoms. It's a monoatomic structure, just one kind of element, copper. On the right, we have sodium chloride. Sodium could be in green, chlorine could be the big yellow or orange balls, or vice versa. Both of them belong to the same group, FM3 bar M. Now it's a face-centered cubic group. Cubic because there's a 3 or a 3 bar in the second location. And this is what the structure looks like. Now, if I look at copper, copper is simple. Let me pull up the space group for FM3 bar N. It's space group number 225. There are other pages to this to these tables belonging to FM3 bar M, but I'm not showing them. They're slightly more complicated. So for the case of copper, we have four atoms at the location 0, 0, 0, and three more atoms at these locations, okay, which represent the center of the faces. So there are four copper atoms per unit cell, and there are 4 points in the lattice per unit cell as well, and there is one atom per lattice point. This is how the structure of iron is built. Okay, now if we look at sodium chloride, let me change the color now. Sodium would have, say, sodium at 4a, and chlorine at 4b. So at the center of the faces, we have chlorine, and at the origins, we have sodium. But the really interesting point is, okay, do you get this? So let me move to OneNote and try to write this down, which I've written in red over here. I'm looking at sodium chloride, FM3 bar M. Sodium is at 4a, and chlorine at 4b. And 4a is 0, 0, 0. But then I need to add the body centered, the face centered locations as well. So this is where the sodium atoms exist. And chlorine exists at 4b, which is half, half, half. And now I need to add the the phase centering translations, which gives me half, 1, 1. So I add this thing to this. Then I have 1, half, 1. Then I have 1, 1 half. So let's draw this now. Cubic. Black shows the sodium atoms. Center of the faces, 0. So these are our sodium atoms. Now chlorine atoms, let me draw them in red. These ions are bigger, so I'm saying atoms, these are really ions because this is an ionic crystal. A chlorine atom here, this thing. A chlorine atom at X is 1 half, Y is 1 and Z is 1, so here. A chlorine atom is at X is 1, Y is half, here. X is 1, Y is 1, and Z is 1 half. So there are 4 of them. So if I just do the translation vectors, I get a chlorine here, 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 chlorine here, chlorine here, chlorine here, here, and so on. So these are really, I can draw all of this in a nicer fashion. In fact, I don't need to draw it. I already have it here. Here you go. This is sodium chloride. Fm3 bar M, and sodium at the location 4A and chlorine at the location 4B. Likewise, I can have more complicated structures. I can have this structure over here. Calcium fluoride. It also belongs to Fm3 bar M. But now the positioning is different. Calcium here and fluorine is at the 8C sites. And remember that there are 4 calcium atoms, and to the 4 calcium atoms, we have 8 fluorine atoms. So the stoichiometric ratio of 1 to 2 in calcium fluoride is satisfied. All right. So the last structure that I would like to talk about today is one of the most beautiful structures that one can encounter. Diamond. F D 3 bar M. And D represents now a diagonal plane. A diagonal plane parallel to the x-axis. And it's going to be a diagonal plane parallel to the y-axis as well, and a diagonal plane parallel to the z-axis as well, because all 3 axes are equivalent in a cubic crystal lattice. Then there's a 3 bar axis along the body diagonal and a mirror rotation, which is a mirror plane, sorry, which is along the diagonal of the face. Okay, so this is what diamond looks like. Now, if I look at the structure of diamond, the diamond, let's pull up the space group for diamond. Here it is. Quite complicated. By the way, if you're talking about this structure Fm3 bar M, there could be some complicated crystal structure in which 192 atoms exist. But they have to be located at these precise locations inside the unit cell. Okay. What we looked at are simpler examples in which only the points of higher symmetry. As you go down this table, you get points of higher symmetry. Points of higher symmetry, which are the special positions, they are populated. So if I have an atom at the 4A locations, the 4A atoms are mutually compatible because of symmetry operations. So you do any of the symmetry operations you can think of in this space group, a 4A atom will go to another 4A atom. It will not jump out of this subspace. So M3 bar M is a subgroup of the space group. And, and these special locations are members of the subgroup as well. Okay. So you can have a complicated crystal structure in which the 192 positions inside this unit cell are populated by the same chemical identity. And very complex and rich crystal structures can arise, which you observe by diffraction studies. But let's move on this last example that we're going to talk about today, and that is diamond. And if you look at diamond, the it's a face-centered cubic cell, and there are atoms at these locations. If I Here you go. There are atoms at the 8A locations. Slightly strange. So I'm blowing it up a little bit. 8A atoms. So only two of them are drawn here because other positions are necessitated by the phase centering condition. So let's draw this. Let's try to draw this here. Okay, and I would like to move to the one node. It's easier to draw over there. So there are atoms, carbon atoms at the 4A location. Sorry, 8A location, 8A, sorry. And they are at 0, 0, 0 and 3 by 4, 1 by 4, 3 by 4. So whenever we draw fractional coordinates, it's even though it's not drawn in the space table, in the space group tables, it's quite conventional to put them in parentheses. So what I would like to do, I would like to draw the clinographic projection. That's easier to draw, looking at it from the top. So there's a carbon atom at the origin, this thing, and a carbon atom. So this is my X, Y, and Z. Go 3 by 4 along X, 1 by 4 along Y, and the height 3 by 4. So there's a carbon atom here. Okay, but then I need to satisfy the phase centering condition as well. What phase centering means is that I need to add half, half, 0 to this. I need to add half, 0, half to this, and I need to add 0, half, half to these points. So let me first add this thing. So this really means that I take this point, X advanced by half, Y advanced by half, and I end up here. Elevation still remains 0. Okay, so now if I were to take this point and add these coordinates, so 3 by 4 plus half, 1 by 4 plus half, and 3 by 4. This gives me a, what does it give me? 5 by 4, 8 by, this gives me 4, 5 by 4. And this gives me 3 by 4 and 3 by 4. Now 5 by 4 is greater than 1, so I move outside the unit cell, but then I could do a translation by -1 and get back into the unit cell. So I'll end up here 1 by 4, 3 by 4, and 3 by 4. So this means X is 1 by 4, Y is 3 by 4, So I get a 3 by an carbon atom here. Likewise, if I repeat, I get an atom here at elevation 1 by 4 and an atom here at elevation 1 by 4. All right. And I will also get atoms here. So this is how I generate all the atoms in the clinographic projection. Whenever I've not written some number with an atom, its elevation z equals 0 is assumed. And if I do write a number, its elevation, that's the elevation above the basal plane. So this is the clinographic projection for carbon. And if I were to draw this, it's what is it going to look like? It's slightly complicated, but you will immediately observe. Let me try make an attempt to draw this in 3 dimensions. I'm just attempting. I may succeed, I may fail. Atoms here. Face centered, right? Now look at these atoms here at an elevation 1 by 4 here and here. So I can draw an atom here and an atom here. So two atoms here and two atoms at an elevation 3 by 4. So, but they are crisscrossing this in this fashion. Now, if I were to draw this or show this on my nice, look here, see here. This makes it really clear. So all of these, by the way, are carbon atoms, even though I've drawn them in different colors, but they're all still carbon atoms. And I've drawn them in different colors because of easy visualization. The orange atoms are at the corners of the unit cell or the centers of the faces. And the green carbon atoms, two of them are at height 1 by 4. So this atom here and this atom here is at a height 1 by 4. Whereas the atoms, this atom here and this atom here at a height 3 by 4, 3/4 of the height of the unit cell. And they are in crisscrossing directions. Okay. And another way to look at this structure is by a ball and stick kind of model, in which you just draw the bonds between the covalent bonds between the carbon atoms. And you will find out that each carbon atom is tetrahedrally connected in the form of a tetrahedron with 4 neighboring carbon atoms. Okay, so this is the FD3 bar M structure for diamond. And I could also look at the different kinds of symmetry planes. By the way, you will observe that there is a screw axis here. 4-fold screw axis here and here. So how could you prove that? You could do a 4-fold rotation followed by an elevation by 1/4. It will take this atom A to this atom B. Okay, by the way, the location of these atoms is one half, sorry. And then another screw operation will take atom B to atom C. So you do a 4-fold rotation and raise the elevation by 1/4. So these two are locations of 4-fold axes. The 2-fold rotation axis has to be, since it's 4 3 bar. So this structure is FD3 bar M. Sorry, D 3 bar m, there has to be a mirror plane which is perpendicular to the faces, sorry, which is along the diagonals of the faces. So these are our mirror planes. So this is a mirror plane here. And what about the glide plane? Now there is also a glide plane. And how do we know that? So if I were to take this atom here, let me change the color. And let me first draw the glide plane. So there's a glide plane at x, y 1 by 8. So there is a glide plane parallel to this picture that I've drawn, but at a height of 1 by 8. So there's a glide plane over here. Below these red atoms, so if I do a side view, this is a glide plane here. This is the base, a glide plane at a height 1 by 8. A carbon atom, a first carbon atom is encountered here 1 by 4. So this is 1 by 8. This has to be 1 by 8 as well. So if I take a reflection of this atom about the glide plane, I will end up at the base. And then what I need to do, it's a diamond plane. D is a diamond plane. What I need to do next is slide by A by 4 plus B by 4. So what this does is that the atom that I'm circling here in red is reflected onto the basal plane, and then it moves by 1 by 4 units along A and 1 by 4 units along B and ends up here. So B ends up at A by the action of the glide plane. Likewise, you could do all your, this point A will end up at this point C because of the glide plane, the horizontal glide plane. And in the same fashion, there are glide planes parallel. So this is a glide plane normal to Z, there's a glide plane normal to X, and there's a glide plane normal to Y as well, because it's a cubic system. So glide planes also exist in diamond glide planes. There's a screw operation in diamond as well. And this ends up my discussion of a really nice crystal structure. I'll give you a homework which exposes other points of this crystal structure, and there are related crystal structures. There's an important zinc blend crystal structure and an important woodsite crystal structure, and probably I'll cover them in the homework problem. And I'll also provide you with the space group tables. Now, if you look at our website, by the way, let me look at our website. I've uploaded all of this information. All of these tables have already been uploaded. So all the lectures go here. The presentation that I showed, important crystal structures, is lecture 5, and I'll upload the video as soon as it is available. The homework is also here. There are two really nice websites that help you look at different aspects of crystallography. And then the handouts for space groups I've uploaded, which were the topic of the previous lecture. The handout on space groups for the most important cubic structures, which I've discussed today, I've also uploaded them. So all of this information is also going on to the website. A second homework will be posted later this week, which will cover different aspects of these important crystal structures. And in the next lecture, we'll shift gears a little bit and talk about how do we determine these crystal structures. And that will be our first encounter with diffraction. When light falls onto these crystal structures, why is it that certain reflections are allowed and certain reflections are not allowed, which means light is diffracted only in specific directions, which helps us determine what the crystal structure is. And most of the work that we do in structural determination of condensed matter systems is through diffraction. That diffraction could be through X-rays, synchrotron X-rays or normal X-rays. It could be through neutrons and sometimes through light as well. So this ends my lecture for today. Sorry, I've just stepped up a little bit over time. Any questions to finish this off?
सर जस्ट वांटेड टू कंफर्म कि जो अभी करंट होमवर्क है वो 5th को ड्यू है कल।
जी 5th को कर लें।
इसको
हाँ सर।
सबमिट कराने का क्या?
दाऊद आपने तो भेज दिया ना?
जी
बस ठीक है। ठीक है।
Sir,
जी जी।
sir, there is a friend who is applying to the science school, और वो overseas पाकिस्तानी है, like he lives in Saudi Arabia. तो अब उसका SSC का टेस्ट भी है मार्च में।
सही।
तो पहले उसने प्लान किया था कि वो पाकिस्तान आएगा और फिर उसने वापस जाके A levels देने हैं। लेकिन yesterday he told me कि सऊदी अरेबिया ने फ्लाइट्स बंद कर दी हैं वापस जाने की। तो अगर वो इधर आया तो he'll be stuck here और A levels के लिए तो वापस नहीं जा सकेगा। तो कोई मतलब डू वी प्लान टू टेक द एसएससी टेस्ट ऑनलाइन या वो उसको आना पड़ेगा इधर?
नहीं अभी वो आ गया, पाकिस्तान आ गया वापस?
नहीं अभी सऊदी अरेबिया है लेकिन ही प्लान्स कि वो एसएससी टेस्ट के लिए पाकिस्तान आए।
ठीक है। और कब है एसएससी टेस्ट?
मार्च की कोई डेट उसने बताई है मुझे।
अगर हादी अगर वो शायद फ्लाइट्स खुल जाएं सऊदी अरब की, मेरे ख्याल में आमतौर पे इनका 10-15 दिन ज्यादा नहीं होता, लेकिन अगर ना ये खुल सकी और उसने अप्लाई ऑलरेडी किया हुआ तो आई एम श्योर लाम्स विल कंसिडर taking an online version or having a test in Saudi Arab or having no
Right.
test at all or having an alternative. So
Right.
we'll manage this, don't worry.
ठीक है, राइट। तो आई हैव आल्सो आस्क्ड हिम टू कांटेक्ट द एडमिशंस ऑफिस, तो वो शायद कोई सॉल्यूशन उसको बता दें।
He can always copy me in email. If I can help, I'll try my best.
ठीक
But
है, थैंक यू
due
सर।
to these force majeure clauses which are outside our control, there is always going to be some accommodation. Don't worry about it.
राइट, थैंक यू।
All right, so I have to meet Bakir and Tawkir. Thank you, everyone. You may leave. Just need to see Tawkir and Bakir. Thank you very much.